Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on August 26, 2025, about 7 days ago. The big contribution is a video inpainting method that removes objects and their side effects like shadows and reflections, powered by a large synthetic paired dataset and a reference-guided diffusion transformer that predicts where those effects occur. The paper is titled, Rows, Remove Objects with Side Effects in Videos, and as we will see later, the results are really impressive. In short, the approach outperforms prior methods and ships a new benchmark, plus a scalable data pipeline using a 3D engine. On X, a post highlights the method's focus on 5 side effects to erase, naming shadows, reflections, light, translucency, and mirror, and credits a diffusion-transformer approach. The clip previews object removal on a green maxed animal. Engagement looks modest, with about 123 likes and a handful of replies. Alright. The previous segment outlined why paired data matters for side effects. Figure 1 presents visual results across 5 categories, which include shadow, reflection, light, translucent, and mirror, and each pair of rows shows masked inputs on top and rows outputs below. The outputs remove both the object and its environmental traces, so shadows vanish, reflections dissolve, lamp glow is corrected, and translucent or mirror artifacts are cleaned up. The consistent backgrounds across frames indicate strong temporal coherence. So the previous figure highlighted qualitative gains across categories. Figure 3 illustrates the 6 side effect types the dataset covers, which matters because training spans these diverse object-environment interactions. The top row shows masks, the middle row shows input video frames with objects present, and the bottom row shows ground truth frames after removal. The columns correspond to common, light source, mirror, reflection, shadow, and translucent, so the taxonomy is explicit and aligned with pixel-accurate supervision. Alright, the previous figure laid out the side effect categories. Figure 2 presents the automatic rendering pipeline that produces paired videos with pixel-aligned supervision, which matters because exact alignment enables reliable difference masks. The top panels show sampling environments, splitting into scenes, selecting an object, and generating multiple cameras focused on it. The middle panels depict automatic masks and mask-based filtering that drops views with too few foreground pixels. The bottom row renders aligned triples, unedited video, masked video, and edited video. Okay, the previous figure described the rendering pipeline. Figure 4 shows the full framework that powers removal, which feeds the entire unedited video and the input mask into a video inpainting model alongside noisy latents. A difference mask, computed by subtracting edited from original frames, supervises a small predictor that learns correlated side effect regions. The model concatenates features for conditioning and optimizes both diffusion loss and mean squared error on the predicted difference mask, so temporal consistency and effect cleanup improve together. So, the previous figure explained the training losses. Table 1 reports quantitative results on the synthetic paired benchmark across 6 side effect categories using PSNR, SSIM, and LPI pages S. The method leads in mean scores, with about 31.1 PSNR, 0.917 SSIM, and 0.077 LPIPS, which indicates sharper and more faithful reconstructions. Category rows show consistent gains, notably highest PSNR for common and translucent cases, while reflection shows smaller margins. Wrapping up, 2 takeaways stand out. The synthetic paired data pipeline unlocks reliable supervision for shadows, reflections, light, translucent effects, and mirrors, and the reference-guided diffusion transformer with a learned difference mask delivers cleaner, temporally consistent removals. This combination pushes video erasing toward practical post-production. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.